This is worksheet 4 of the States of Matter packet, where we're going to focus a little bit more on specific names of intermolecular forces. So just some background quickly. Maybe you've heard this before, but any object that is in motion has an energy that we call kinetic energy. So kinetic energy is just energy of motion. And even though we use the word temperature all the time, what temperature actually really means scientifically is the average kinetic energy of all the molecules in a sample of matter. So if I have molecules of H2O that are forming steam that's at 100 degrees Celsius, and I have molecules of H2O that are in a block of ice that's at 0 degrees Celsius, what the 100 degrees and the 0 degrees is actually telling me is how quickly the molecules are moving. So they're moving a lot faster in the steam than they are in the block of ice. So if you start thinking about this idea, this definition of kinetic energy, you might come to a very good question, which is, okay, so if I have a bunch of molecules at room temperature, that means they all have the same kinetic energy, right? So they should all be moving at the same speed, but why is it that some materials are gases at room temperature, right? And others are liquids at room temperature, and others are naturally solids at room temperature, right? We look around a classroom that's at room temperature, and some things are gas, like the air, and some things are liquid, like water, and some things are solid, like our desk. So why is that? Well, we have to think a little bit about the specific types of intermolecular forces that are holding together the molecules in those different materials, and that'll be our answer. So a little reminder of some terms that we talked about in the covalent compounds packet. It's worth a reminder because they sound so similar that students tend to mix them together, okay? In the ionic and the covalent compounds packet, we talked a lot about intramolecular forces, bonds within one molecule. So these are bonds that hold individual little atoms together, right? Like hydrogen and oxygen form a covalent bond in a water molecule, okay? Those are incredibly strong forces, okay? We don't have the ability in our basic lab in our classroom to separate a hydrogen and an oxygen within one molecule of water. Right? What we haven't talked about and named as specifically, right? We know how to talk about ionic bonds and covalent bonds. Those are all intramolecular forces. We have not talked about intermolecular forces as closely, right? So far, all we've said is that intermolecular forces are forces between multiple molecules. So this is more of like a big picture force, right? It's a little bit more zoomed out. So this is a force that would hold two whole H2O molecules together, right, and make water sort of stick together as a substance, okay? These are much weaker, okay? So it's the intermolecular forces that are much stronger. The intermolecular forces are weaker. And I want you to have that in mind because now what we're going to do is we're going to kind of set aside intramolecular forces and we're going to really zoom in on 3 specific types of intermolecular forces. And so we're going to be ranking of these 3 intermolecular forces, which one is the strongest, which is the weakest. But it's important to keep in mind that no matter how strong an intermolecular force is, it's never as strong as an intramolecular force. Those covalent ionic bonds, they're just much stronger. Okay, so that being said, there are 3 intermolecular forces that you need to know, okay? I'm actually going to skip over the dispersion forces. They can be a little confusing. I'm going to start with dipole-dipole forces, okay? You're going to make your paper look like mine. So the example of a dipole-dipole force that I'm going to use is a carbon dioxide molecule. So a force that holds multiple carbon dioxide molecules together. Carbon dioxide is a gas at room temperature, right? And if we draw a picture of it, and I want you to do this, now you would be able to do this on your own, hopefully, because we talked about this in the bonding packet, but we'll speed things up a little bit, okay? Here's what carbon dioxide looks like, all right? Now, just looking at this, you can kind of see it seems like there's a lot more electrons over on the oxygen side of this molecule than on the carbon side. And if you look at the electronegativity table on the previous worksheet, right, that sort of ranks how much each different type of atom pulls electrons towards it, oxygen has an electronegativity of 3.5, carbon dioxide only has an electronegativity of 2.5, right? So that means that in a tug of war, oxygen is going to win. It's going to pull the electrons closer to it, okay? So what that also means is, if you were to look at that double bond between carbon and one of the oxygen atoms, doesn't matter which double bond, the electrons wouldn't be all nice and happy right in the middle between the carbon and the oxygen. They'd be more over on the oxygen side. Okay? Oxygen doesn't share super well. It's trying, but it wants the electrons a little closer to it. Okay? So, what ends up happening is there's more electrons over on the oxygen side of the molecule, and so that oxygen side of the molecule is a little bit negative because electrons are negative, right? It's not a full, complete negative charge. It's a little bit negative. Okay, so we use this funny symbol. It's kind of like a fancy cursive S, and then a negative sign to say, okay, oxygen's not completely negative here, right? It hasn't totally ripped the electrons away from carbon. They're still sharing, but it's got the electrons a lot closer to it than carbon does. Okay, and so this oxygen's kind of doing the same thing. And then this carbon over here, as a result, it's gotten its electrons kind of pulled away from it, ends up being a little bit positive. Okay, so that fancy S just kind of means a little bit. A little bit negative on the oxygen side, a little bit positive on the carbon side. Okay, now we've got a bunch of carbon dioxide molecules all close to each other. So let's draw another one in here. And let's think about what's going to start to happen. Okay, same thing over here. Carbon's a little bit positive. The oxygens are a little bit negative. Next thing you know, there's kind of an attraction between the negative end of one of the sorry, I'm changing colors, so I'm distracted. One of the carbon dioxide molecules and the positive end of the other carbon dioxide molecule. So you get this little, I'm going to draw with a dashed line, little attraction between this negative end and this positive end, because opposites attract, right? Okay? So that separation of charge, that difference that the carbon side is positive and the oxygen side is a little bit negative, we call that a dipole. Okay, so since each of these carbon dioxide molecules has a dipole, we call this attraction between them that's going to hold them together a dipole-dipole force. Okay, and dipole-dipole forces are strong, right? And they're between the positive and negative ends of these polar molecules, right? These molecules that don't share their electrons really equally. All right, so that's that. Now, there's a special type of dipole-dipole force. Okay, so this isn't its own intermolecular force. It's really just a special type of intermolecular force that's called a hydrogen bond. Okay, like go figure, because hydrogen is the baby of the periodic table and it's always got to be special. Okay, so when you have this attraction between two polar molecules, but one of the molecules contains hydrogen, we don't just call it any old dipole-dipole force anymore. Woohoo, we have to call it a hydrogen bond. So let's draw a little picture. Let's use water as our example. It's a classic molecule that has hydrogen in it. Okay, so here is our water molecule, right? You've drawn this before. And sure enough, if we look at our electronegativity table, water has an electronegativity, or excuse me, oxygen has an electronegativity of 3.5 and hydrogen 2.1. So that oxygen, yeah, it's sharing electrons with hydrogen in that single bond there, but it's keeping them over on its end. So the oxygen is a little bit negative, and the hydrogens both end up being a little bit positive because they've had their electrons kind of pulled away from them. Okay, and so if you have another water molecule nearby, and it's doing the same thing, right, we're a little bit negative here, a little bit positive here, right, you can start to see what's happening. Okay, we have the negative over here, the positive end over here, opposites attract, right? And so this is what we call a hydrogen bond, or sometimes you'll hear me say just an H bond. Okay? This is a type, a special kind of dipole-dipole force. Okay, so if I tell you something's a dipole-dipole force, but the molecule has hydrogen in it, then you go, oh, okay, it's a hydrogen bond specifically. It's a type of dipole-dipole force. Any other dipole-dipole force that doesn't have a hydrogen involved, we just call a dipole-dipole force. Awesome, right? Hydrogen's so special. Okay, but the thing is that these hydrogen bonds are really, really strong. They're the strongest of all the dipole-dipole forces. Why is that? Because hydrogen is so teeny tiny that oxygen can like really crank on it. It can pull really hard on that hydrogen, right? I mean, it's like if you're in a tug of war, literally, and you look over and the other team is a bunch of like teeny tiny, like, you know, 5'2" little girls, like middle school girls. They weigh like 95 pounds each, right? You're going like, oh, this is good. We're going to really be able to win this tug of war, right? Well, in a hydrogen bond, that's what oxygen is thinking over here. It's like, oh, that oxygen or that hydrogen's tiny. I'm going to really pull hard on it. So it makes for a really strong force. Okay. So the last type of force, and this is not a dipole-dipole force at all, okay? Remember with the dipole-dipole forces, we had two polar molecules, right? They were polar because oxygen was pulling harder on its electrons than carbon. So the electrons were scooted way over to one side, okay? Well, what happens if you've got nonpolar molecules, right? Let's think about oxygen gas. Oxygen gas is made up of two oxygen molecules, okay? And look at it. It's like a super symmetrical molecule. Oxygen, you know, is just two oxygen molecules. Like, they each have the same electronegativity, 3.5, right? One of them's not going to be able to pull harder on its electrons than the others. So this is like the tug of war that will be just permanently tied, okay? So you can't draw, like, these little kind of negative, kind of positive symbols like you did on a polar molecule, right? These are nonpolar. Okay, and then over here you got another one, right? Because like oxygen gas isn't made up of just one oxygen gas molecule, there's a whole bunch, okay? But this one's just as nonpolar, okay? But here's the thing that happens. It's a gas, right? So these electrons, they're like moving all around, and right, electrons sort of buzz around like little bees around a hive. And so every once in a while, just sort of like by chance, you can have this like temporary, momentary, weird, off-chance moment where like a bunch of electrons, let me pick a color here, a bunch of electrons maybe end up like, whoop, shifting over here. Okay, and so you just get this temporary, teeny tiny little kind of like collection of electrons on that double bond over on this side. Okay, and maybe at the same moment, that's why this is like such a weak thing. It's like only happens just by chance. Maybe some of these electrons in this double bond, just as they're moving around, like whoop, all happen to be over on that end, right? Just like fate. This was just like meant to happen. Star-crossed lovers, who would have guessed, you know, and like the stars all align and their electrons end up both on sides near each other, and then like all of a sudden there's this little attraction between them. Okay, and that is what we call a dispersion force. Or sometimes we call it a London force because the guy who described it, guess what his last name was? Go figure. Okay, so these are like very weak. Okay, because it's just, you gotta just like the stars all have to align for this to happen, and it's like fleeting, and then the electrons move again, and the magic is gone. Okay, and this happens to nonpolar molecules. All right, so the forces holding oxygen molecules together are much weaker than the forces holding carbon dioxide molecules together, which are still even weaker than the molecules holding water together. Okay, and so that's why at room temperature, water is a liquid with its molecules pretty close together, and carbon dioxide, right, is a gas, and oxygen is also a gas. But as it turns out, if you want to get carbon dioxide to solidify into a liquid, to condense into a liquid, it takes a lot less energy than it does to try to get the oxygen gases to solidify, or to condense into a liquid. Okay, so it really all comes down to their intermolecular forces.